So my lecture would be some overview that starts with automatic verification and continues into code synthesis. And I chose this picture, so I think a lot of you would recognize monument values, because I want to describe some of the nice monuments of automatic verification, which we call model checking. And I hope the picture would be beautiful, of a kind of nice landscape. And then you'll see how I connect it to the future, to automatic code synthesis. So since the early days of software development, people were really concerned with the correctness of code. One example, which we often give, is the explosion of the Ariane 5, kind of on his maiden launch. There was some error due to something with the size of representing an integer, and it's just exploded. On the right, you can see a picture from the movie Western World, where people are concerned that robots would take over and they would start to kill people. And this is documented a lot in this fear in the literature. So people really want to have correct software and also hardware. And this is kind of, if my history would start from the 1980s, then what happened in the prehistory? So it's not completely a desert, as in the picture, but what it is that there were some very interesting, important works, mainly about the manual verification of programs. So I think Bob Floyd was although some people say that Alan Turing already was concerned with the verification of software, but Bob Floyd was probably the first one to suggest a proof system for programs. So he suggests a way to annotate flowcharts with invariants, and to prove that the invariants are consistent with the code, and therefore he could prove partial and total correctness of programs. Tony Hoare came with something very nice. He extended first-order logic by putting the program into the logic. So what we call the Hoare triples. You have some precondition, postcondition, assertions, and pieces of code, and you have a proof system, also very beautiful. Owicki and Grease extended all of that to concurrent programs. And these methods are all manual-based, okay? Amir Pnueli, in 1977, came up with a very interesting idea that when you want to say something to specify properties of programs, then really you want to specify not only the initial and final conditions, but you want to say something about the way the program reacts and what happened throughout time. So he suggested to use the linear temporal logic as a specification formalism. Some of these works, like Pnueli's work, awarded them the Turing Award eventually. And this is kind of the prehistory of 1980. What happened in 1980, 1981 is very interesting. There are two groups or two couples of people, one in the US, Clark and Emerson, and one in France, Quay and Sifakis. And they come up kind of simultaneously, and I think they argue until today who was the first and whether one was influenced by the other, I don't know, they might, of the idea of what we call today model checking. I don't think they call it model checking, but they talked about the automatic verification of systems. Okay? And their ideas are quite similar. I'm going to talk a bit about the initial ideas. So here are the main principles. It's all in one slide, but I have to explain it slowly because it's kind of, the slide is very full. So the main idea is that it's a finite state system. So if you want to verify, like in Hoare and Floyd systems, proof systems, then it doesn't have to be finite state systems. But what they thought of, well, let's limit it to finite state system, and then maybe it's decidable, maybe it can be done by an algorithm automatically. So first of all, it's a finite state system. This is most important. Then it's an issue of modeling. So you have a piece of code. It could be sequential or concurrent program. And let's see if I can do this magic with Microsoft. So let's say I have this piece of code here, highlight, okay? And this basically is a little program that does in kind of a very simple way mutual exclusion, okay? So it consists of two processes. It's symmetric, and they use some variable, which is called turn, to prevent both processes to get into the critical section at the same time. The critical section is the thing highlighted with yellow, okay? And they have to take turns, so it's not the most clever idea or algorithm. Of course, it's not a reasonable one. But what I'll do now is I can translate mechanically, I can compile that into a set of transitions. So there would be 6 transitions, as in the right of the code, okay? And the transitions consist of an enabling condition, a condition that tells me where I can execute the transition. The transitions are atomic. And when the enabling condition hold, then I can execute the transition, which means a transformation. It's an assignment, possibly assigning values to several variables at the same time. Why several variables? Because the program counter is also a variable, and usually a transition also changes the program counter. So if I make a simple assignment, then I assign a variable and I assign a new value to the program counter. So it's very simple. And then what I get is I get a state graph. Okay? And it's a finite graph. Okay? It's a finite graph. The states are the values of the variables, including the program counters. And the transitions, well, they correspond to my atomic transitions. Some of them I mark, like going from that state to that state. I fire transition T3, okay, which is here. This is T3. And T3 correspond to moving from the head of the loop here to that transition, which is marked as non-critical in the code. Okay, so basically it's a modeling issue. It's very easy, and you can translate from code to transition using a compiler. You can translate from transition to a state graph by basically using depth first search, right, or breadth first search, or whatever. You know, you start from the initial states, so you have initial conditions, and so I have here 2 initial states. This is one, this is another one, and then I apply the enabled transition to find their successor and their successors, and it has to terminate because it's all in finite states. So this is the main modeling issue. Okay? And that works well for interactive programs, for concurrent programs, for sequential programs, for everything. All the transitions are in the same pile, and this is very easy and simple. So now that the question is of the logic, which logic I'm going to use, and in this lecture, I would use linear temporal logic. And in fact, this is not as per the seminal work of these 2 groups of people, of Clark and Emerson, Crane, Sifakis. They use another logic, which is called computational tree logic, which looks at, you know, a tree of executions. And my logic, linear temporal logic, the one I would use is due to Pnueli, or Pnueli is the first one who used it for verification in computer science. And what it looks at is at the execution sequences. So what is an execution sequence? If I go back to my graph, an execution sequence is basically every maximal sequence that is initialized with an initial state. It starts from one of the initial states, and then it's maximal. It's a path that goes through that graph. Okay, that's an execution sequence. And if you look at this graph, then there's infinitely many sequences. And a program satisfies its linear temporal logic if basically all of its executions satisfy the temporal logic specification. And I have some modalities. The logic consists of the Boolean operator and, or, not. It has propositions corresponding to some properties of states. And it has some modalities, like eventually or always. So eventually means that something happened at some point in the future in the sequence, and always means that from some point on, it holds in every state or starting from every state, and there are other modalities. I'm trying not to be very technical because I know not all of you come from formal methods, and therefore I try to just give the intuition of what we're doing here. So for example, if I look at this property here, which reads box diamond requests, arrow box diamond granted, really what it means is that if from every state, okay, if always, the box means always, from every state there would be a future point where I make a request, it also means that I make infinitely many requests, then I make infinitely many grants, okay? So if there's some system where there's no limit to the number of requests that are made, then they're always granted. And this is a typical linear temporal logic specification. And I want to verify that. Okay. So here are some nice properties of that logic. First of all, this logic is equivalent to monadic first-order logic. Okay, so I could translate back and forth between this and a logic which consists of variables corresponding to the time points. Okay, time points are like the places, the states in the execution sequence, and I can translate the predicates into the predicates in the temporal logic into monadic predicates with on a time variable in first order logic. So these are equivalent, which is very nice. I have a very nice characterization. Okay? So again, let me take a property which looks very similar to the one I showed in the previous slide. It says, oh, if always eventually process P is enabled, can allow some transition to execute, then always eventually the process P gets the chance to execute. That corresponds to what we now call fairness. Okay? We're fair to each process, and we may want to require that from an execution. And this logic has lots of advantages. One disadvantage it has is that you can express immediate choice, but in the long run, there are some properties depending on choice which you cannot express. For example, what is called home state, the fact that the system always have the possibility to return to a home state. Say if you put your ATM card into the ATM machine, whatever you do, eventually you can force the system to say, hello, please put your card into the ATM machine. Maybe it swallowed your card, but the next customer will be able to put the card so that he could get money. Okay, this is a home state. You cannot express that with LTL. And in fact, these groups I showed before, they work with another logic, which is called CTL. It's a logic not on executions, but on a tree. There, it's easy to say that property, but you cannot express fairness. There has been 35 years of wars between people that like this logic and not that logic. And also, there were smart people that say, how about we have a lot of expressiveness by having a logic that contains both. So there's a logic which contains both of them and even more. And why not use that? Because there are trade-offs. The more expressive you get, the more difficult algorithms you get. Okay? You pay for everything. There's no free lunch in this business. Okay, so what we need to do, so I try not to be technical. I mean, I think this is the only technical slide in my lecture. What we do is how to check LTL properties. And in fact, LTL properties are slightly more complicated than to check these other guys' logic. This other guy logic, that would go state by state. And sub-properties could be calculated first. LTL, I need to do something like that. First of all, I would translate my specification into an automaton, okay? And then what I have is two automata, because my state graph, which contains all the executions, is actually an automaton, right? So you can look at it as generating the execution sequences. And I have an automaton that basically generates all the executions that are accepted by the specification, okay? And now what I need is to compare them. I need that all the executions of my state graph are included in what my specification allows. So it's a language containment, right? Well, we'll get to that in a moment. Language containment actually is difficult. So we'll get around that. But basically what I need is a translation. And indeed, whoops. That's not what I meant to do. Sorry. So indeed, what we have is we have a first translation algorithm, which is very revolutionary, by Vardy and Wolper, and that gives you a translation from LTL into automata. Let's talk a bit about this automaton. And actually, here's another translation. This is by Rob Gareth, myself, Vardy, and Wolper, which the improvement is that there's kind of an on-the-fly algorithm that generates much smaller automata. The correspondence in size between the LTL specification and the automaton is exponential sometimes. And in the Vardy-Wolper algorithm, it's always exponential. It gives you an exponential blowout. The automaton is exponentially bigger. The number of states is exponential in the size of the LTL property. In the Gareth-Peled Vardy-Wolper algorithm, it's often linear. In the worst case, it could be exponential. So this, I think, is almost de facto algorithm that people are using. And so what kind of automaton do I need here? So in fact, I need finite automata, but it's not the usual finite automaton. It's an automaton over infinite executions. So my acceptance condition cannot be that at the end I would reach an accepting state, because there's no end. Don't worry that this is automata over infinite words. I'm not going to execute them. The automaton is just a model, and it's a graph. And I can process that to do model checking. I never wait indefinitely that the execution would terminate. So my acceptance condition of infinite words is that I have accepting states, that these are the red states, and I have to see them infinitely many times during an accepted execution. Okay? So on the left, I have here an automaton for the property always eventually P. And as you can see, this automaton, the red states are accepting here. So I have to see infinitely often the state S0 so that I accept. And each time I see S0, what would happen is I get there with an edge which is marked by P. So it means infinitely many times I see P. And this is always eventually P. On the right-hand side, I have an automaton for eventually always P. And here, what happens is that there's only finitely many times in which I do not see P. And this is a non-deterministic automaton, as you can see. So the left state S0, I stay there until I guess I saw the last not P. Then in my guess, I go to S1, and if I don't see any more not P, then I stay there, and obviously I see S1, which is accepting infinitely many times. Okay? The fact that I use a non-deterministic automaton, you may say, is odd, right? Because in finite automata, non-deterministic automaton could be translated through the subset constructor to a deterministic automaton. We cannot do that with, I'm not going to show a proof, but we cannot do it with this kind of automata, which we call Bushi automaton. Okay? There's no equivalent deterministic Bushi automaton. Model checking doesn't care about that. When I'm going to talk about synthesis, we'll see that this is a bit of a problem. Okay? So I think this is the most technical thing in my talk. How do I check LTL properties? Okay, so as I said, the state graph is an automaton. It corresponds to a language. The specification is the language of the executions sequences that satisfy the property, or the executions which are accepted by the automaton. Okay, and I check language inclusion between these two. Okay? Language inclusion is very hard, in particular when one of the automaton, the one which you need to be included in its language, is non-deterministic. Okay? In fact, it's p-space complete. We don't care. It's complicated. So in fact, what I do in practice is I'm saying, okay, well, determinizing, there's no deterministic equivalent, as I said in the previous slide. I cannot determinize. Can I complement? Complementation of a Bushi automaton is very difficult. Also, if it was a finite automaton or finite words, also very difficult. It can have exponential explosion. But I have a trick. So instead of translating the property into automaton and complementing, I would negate the property that corresponds to the complement property, and then I would translate. Then I get the complemented automaton. Now I have, instead of language inclusion, I have an intersection problem. if the intersection between the executions and the bad property, the bad executions, those that do not satisfy the property, is empty, that's good. I don't have any bad execution. And if it's not, then it's good because I found a counterexample. And this is model checking, right, in several slides. This is basically state-based model checking. Okay? For example, if you look at the spin model checking system, then it basically works exactly on these properties. So here are some observations. So this is very nice in theory, but if we look at an actual system and do something based on that, check for emptiness of the intersection, basically this would reduce to some depth first search on some product of two graphs. There could be millions, billions, trillions, gazillions of states, and it's not practical. Okay? Although the spin system basically works like that, for very, very large system, you have to do something. Okay? So we need some reduction that would reduce the number of states, or we need some kind of representation that would allow you to work on many states at the same time. You cannot just, the state-based approach is nice, but in practice is not going to work. Okay? So I'm going to explain, very briefly some of the main ideas that people came up. I think these are very beautiful ideas, and I'm not going to be very technical. So it's going to be just kind of an overview to give you the idea, kind of the intuition, and it's sufficient if you see how beautiful these ideas are without, making proofs or understanding exactly the idea. First of all, one way of reducing the number of states we observe or the number of transitions is based on a very nice observation, which is that if in finite state systems, based on this kind of specification, Bushy automaton, which are the translation from LTL, I have a counterexample, then there's always one kind of counterexample that exists. So I may have different kind of counterexamples, but if there is a counterexample, there's also one of this form. It has a finite prefix, and then it has a cycle. It's actually a cycle across the acceptance states of this automaton, but this is just a technical issue. So it's a prefix and it's a cycle. There are different names for that. Some people call it, like, a French mathematician call it ultimately periodics. Americans call it lasso shape. So this is American model checking. You can see you try to use a lasso to find some bugs. And this is a picture by Ashutosh Trivedi. Okay? So what we do there is we have a very interesting algorithm. So instead of using a depth first search, we use a double depth first search. First depth first search for an accepting state. And the second depth first search, look for the cycle. Okay? It's not exactly in that order because the second one starts when we backtrack to the accepting state. Otherwise, it wouldn't work properly. We would lose some sequences. And the basic algorithm is by Korkubaitis, Vardi, Wolfer, and Yannakakis. The nowadays use is by Holtzman, myself, and Yannakakis. And the improvement is that we're not actually looking for a cycle through an accepting state, but we're looking for a path from an accepting state back to the stack of the first depth first search, and that would close the cycle. That's much more practical because the chance that you find a cycle back to your own state is very slim. And why is it called on the fly? Because once we find such an ultimately periodic cycle, then basically we're done, and we don't have to repeat. We don't have to explore the entire state space, and usually this is done much, much before we we completed the state space search, provided that there's an error. So model checking basically is more about finding bugs than to verify. Because if we didn't find a bug, it doesn't mean it exists. Maybe our specification is not strong enough, etc. Here's another idea, and which, Mats mentioned the cover word, so there's a picture from the ceremony, is another idea. And we had also a competition there between several groups. One consists of myself, one is Antti Valmari, and one is Godefroy and Wolper. Okay? And here are four of us in the picture. So the idea of partial order reduction is that mainly in model checking, we're interested in concurrent programs. Okay? Because it's more challenging and you have much more errors when there are independent things happening. But when independent things happen, like here, let's look at these 4 states. So if alpha 1 and beta 1 are happening concurrently, usually that means that they're independent. So if you do alpha 1 before beta 1 or beta 1 before alpha 1, it doesn't matter. The idea of partial order reduction is I don't need all the executions. I only need an ample set of execution, an ample set of successors. So calculate from every set an ample set of successors that you need, and that should guarantee the correctness in the sense that I have enough representatives. So if I have an error, I have them in one of the representatives. The equivalent executions, those that I remove and those that I do not remove, equivalent executions, I cannot distinguish between them in terms of the property I check. So it depends on what property you need, and there are different kind of methods. And as I said, I'm not going to be technical and tell you how I calculate the ample set of successor from each state. But depending on the property, I may say want to check all the states. You see, so my reduction would consist only of some transitions, which I'm not going to take. But in fact, my property may be such that I don't need to distinguish between whether I do the alpha transitions before the beta transitions. And then a lot of times, I need only one execution that represents everything. That's the extreme reduction, okay? So automatically, this method tries to say, okay, given a state, don't explode all the successors, calculate an ample set of successors and continue like that. And spin actually also has this idea. He used to have a patent on that, but I think it's expired by now. Here's another interesting idea. In fact, it works better with this logic of these 2 groups from the 1980s, less well with the LTL. But the idea is that representation, instead of working state by state, just take a set of states and represent it in a very compact way, which is called binary decision diagram. Okay, it's a compactness of a binary tree, which represents a set of states, and then apply each transformation from a set of state to a set of states. So don't go through every state and calculate its transition. Keep a set of states and calculate their successors in one fell swoop. So you get a representation, a BDD, binary decision diagram, calculate the successor. It's another BDD. Continue doing that, and then typical papers or initial papers on this area had some very big numbers in their title, like 10 to the power of 20 states and beyond. And if you consider the fact that model checking is actually a p-space complete problem, then obviously it doesn't mean that every system with 10 to the power of 20 states you could really verify in this way, but it means that a lot of time you can. Okay? And some typical examples like multipliers would not reduce themselves easily, and in fact, BDDs would not make any reduction, but a lot of times if you have big systems, then this is the way to go. Here's an example, like the tree on the left is just the binary tree representing a Boolean formula, and each solution, each satisfying assignment is basically a state. Okay, so a state basically is a sequence of Boolean variables. Okay, and the diagram, the directed acyclic graph on the right is the compacted version, the BDD that correspond to the left. And then if I want to find the successor of these states, I would do some kind of a transformation, and I have another BDD and another BDD, and I do a lot of things at the same time. I am going to work with a lot of states in one fell swoop. This is wonderful. Here's another interesting idea. So at some point, SAT solvers became extremely efficient. Okay, so like a magic, suddenly we can solve an NP-complete problem with lots and lots of variables. I mean, amazing. And then what I can do is I can encode my counter example basically as a Boolean formula. So this is a simple counter example which goes from the initial state, say, to some final state that satisfies some property. But in general, instead of encoding a path, I would encode the lasso. Okay? And so my encoding, what it says, it gives me a Boolean formula. I actually write the Boolean formula itself. says this is an initial state. This corresponds to the initial state. And this is a Boolean formula that tells me that the second state is a successor of the first state. And this is a Boolean formula that tells you the third state is a successor of the second state, etc. It's a big conjunction. I throw it to a SAT solver, and magic. SAT solving is so efficient. I mean, there's all kinds of questions why that would work. I mean, in fact, the counterexample could be exponentially bigger than the description of the system, so it doesn't mean that it always going to work. In fact, all of these methods, because of the complexity, really choosing the right method and making it work, it's not completely automatic that everything works for you and it's easy. Okay? And from that, there's an idea of satisfiability modulo theory, which does the same idea, applying it to infinite state systems. Okay? Infinite state system or decidable theories of infinite state systems, which you can apply SAT solvers to them. Here's another idea. You can apply abstraction. So the idea of abstraction is you map lots of states into one state. So if you look at the system, this is a traffic light on the left. It has 3 states, and 3 states is too much. I have only two states, only one bit. So on the right, I map the go states into go and the stop states into stop, okay? And it's a homomorphic mapping, and therefore for every execution on the original system, I have an execution on the abstract system, and the abstract system is much smaller. Unfortunately, there could be false negatives because of the homomorphism. It's not an isomorphism, and therefore I may have false negatives. So if I found a counterexample checking the abstraction, then what I do is I have to compare it and see if it's a real counterexample. And if it's not, then there are methods that automatically would tune the abstraction, would give you a refinement of the abstraction, and therefore you have possibly more states, but it would be more accurate, and eventually you find the counterexample. In fact, that process of abstraction is what people usually do, you know, in their head. So if you send someone that wants to verify something with spin, usually is not going to do that, but he would abstract away a lot of things and give you a reduced model, okay? And then he would try to justify, and if he finds a counterexample, good, this is good abstraction. And if it's not, then how does he justify that this is not done automatically? But in practice, this is what people are doing, okay? They're kind of abstracting all kind of things from the system and producing a model, not automatically. So there are many other ideas. Like people use interpolation method in like creating interpolation to speed up the search. Some people have model checking for a recursive system or one automaton system. For 2 automata, it's undecidable. People have model checking for real time. For what we used to say hybrid system, now we call it cyber physical system because the new name is good for getting funded for research. Probabilistic systems, etc. There's lots of systems, and there's lots of tools, okay? So there is the spin tool, and I worked a lot with Gerard Holtzman in Bell Labs, so we had a lot of patents, which, like for the partial order and for the translation of LTL, which I mentioned, and for all kinds of things, like the double depth research, we had patent on that. I think they're expired now. And this is a state-based model checker. SMV comes from Ken McMillan. This is based on the BDDs that I explained. CBMC, it's software model checking using SAT solver, which I mentioned. PRISM comes from Oxford, Marta Kwiatkowska. This is a tool for verifying probabilistic systems. UPAL is, Uppsala Aalborg. It's a Swedish-Danish collaboration. It's a tool for time system. Kim Larsson usually is associated with that. And there are many others. People are very touched if I don't mention their own research and tools, so I apologize. I just put some of them. And in fact, if you look at companies, big software houses like Microsoft and big microelectronic developers like Intel, they always have in-house teams that try to produce methods, that try to learn methods of others, that either adopt methods of other groups, or develop their own methods. And in fact, I don't think nowadays there's any real big company that does not use model checking. We still use testing as the main software reliability method. Okay? So what we observe, there's no technique that works uniformly for all the cases in model checking, so you still have to have kind of the man in the middle that would kind of tune, would abstract, would find the method that is best to work with. There are many trade-offs. Like if you have more expressive, then higher complexity. Okay, if the property, you find a way to represent the property with a shorter formula, a lot of times the algorithm becomes more complex. And in fact, we have the principle of no free lunch here. Okay? The problems exist. Okay, and there's growing community. There's now a lot of conferences that look at that, and within software engineering, within model checking, testing is being connected to model checking, automatic verification. They are kind of mixed method of testing and verification. Let me talk a little about automatic synthesis. Instead of the loop of finding or trying to find a counterexample, sending it back to the developer, fixing the system, model checking, trying to find a counterexample, why not immediately take the specification and translate it to a correct by design working system? Okay? Why that didn't work so far and why it starts to work. So the old classical approach, okay, we start to see that we actually with the Emerson-Clark group. So the 81 Emerson-Clark paper was about synthesis, a bit about synthesis, how they discovered the model checking idea. Emerson was interested in synthesis, in fact, okay? And basically, to them, synthesis meant translate the property into an automaton or into some kind of representation, and that basically is translatable into a piece of code. Okay? And if you look at other papers, like there's the work of Mana and Wolper, again, they said, okay, we want to synthesize a solution for a specification given in linear temporal logic. So we translate it into a Buki automaton, okay? We make sure that, we translate that Buki automaton into software. And since we want a concurrent system, then we take the projections for different processes. But how do we make sure that independent things work? We need a scheduler. Unfortunately, this approach gives you something which looks like concurrent, so it's distributed, but it's not really concurrent because the scheduler would make an order between things that should happen concurrently, make sure that the order consists with the property. This is not really synthesis as we see it today. So I said this is the old classical, and this is the new, but still classical method. The new classical method looks at two kinds of system, interactive system and concurrent system. Interactive system, I can describe it as a loop. The system, or I am doing something, and then, I emit an output to the environment, and I get some input from the environment. The environment responds, and I do something, the environment responds. So we alternate, okay? And here's the challenge. So I have a linear temporal logic specification, and the outcome of this interaction should satisfy the specification. But I have control only on what I do. Okay? So I have to guarantee that I do something, and reacting to the environment, I do something else. I don't know what the environment would do. I cannot block it from doing anything. Still, the outcome of both of us would correspond to satisfying linear temporal logic property, or Buki automata property, or whatever property you have. Okay? And how do I do that? Okay? The specification is linear temporal logic. This is the challenge. How do I do that? Okay? So here's the classical method. So the classical method does translate the specification in such a way that it would enforce the specification on the combined system and response alternation. So I can describe it as a game, right? So I'm playing against the environment. I am the system. I'm playing a game against the environment. And let's suppose that the specification would be that I would reach some state at the end that would satisfy some property. okay? And this is simple, because this is basically a reachability game. And we know how to solve reachability games, okay? So this is basically just like, I can use min-max, right? Min-max algorithm. I would say the states which I reach, the good states would have value -1, the good, +1, the bad states are -1. I do a min-max, and in fact, the strategy I get by the min-max algorithm is the synthesized system. Okay? It's the synthesized behavior. It will tell me if I can reach a good state, and it will tell me what to select at each point. I have many choices what to select. Okay? Unfortunately, I'm talking about temporal specification, and therefore, alas, it's not a reachability game. It's a game based, on infinite executions. I'm not going to be technical to do that. It's still a game. It's more challenging. I have different kind of strategies, but I still have to find a strategy. The strategy is the system that I'm going to synthesize. It's very interesting. So what I need to do is translate, say, the LTL specification. I get an automaton. Alas, it has to be deterministic, because my rival, the environment, can play against me, and if there's a non-deterministic choice, it can take advantage of it. So I have to determinize. That's unfortunate. So I first translate, then I determinize. Alas, I cannot determinize a Bushy automaton. We saw that. So I need something more complicated, and there are automata of more complicated acceptance condition, street automaton, Raven automaton. I'm not going to talk about that, but I need to do that and to use them. Then I find a strategy. How expensive? Translation is exponential. Determinization is also an exponential. It's not always the case that two sequential exponential procedure, one on top of the other, needs to be double exponential. Unfortunately, this is the case here. So synthesis is doubly exponential. And indeed, I can have a system which must need doubly exponential number of states in the size of the temporal specification. So, this is the complexity, but in fact, it really means that linear temporology is kind of compact. It could represent a system with double exponentially many states over the size of the specification. I'm not going to show that. Okay, this is another reason I chose the picture at the beginning. So there's a scene in Forrest Gump where he runs by chance on the same place I was standing. I didn't know that until I returned and showed my son this picture. And then he gets some kind of wise comment from his mother. His mother is always very wise and says, Mama always said, put the past behind you before you can move on. I'm going to talk very little, a few minutes only, on a method that I used or I developed with my student. But the principle, the different principle I think one needs to apply to program synthesis is that you need to look in a different direction. And one idea is, okay, synthesis, as I presented it, synthesis is doubly exponential. Synthesis of concurrent programs is undecidable also. It's even worse, okay? So what I'll do is I'll try to use some heuristics. And also, I try, perhaps instead of translation, I'm going to use model checking, which I explained before, as a feedback loop. So I generate and test, or actually generate and model check. I keep generating things or candidates, and I'm going to check them. Okay? One additional idea is I can limit the size of my system. So I would check system up to 2 states, 3 states, 7 states, I don't know, 18 states. Maybe I would double it. But if it's finite and I do I limit the number of states, then it becomes decidable, even for concurrent systems. Okay? So there are different methods. One was really, Gadi Taubenfeld and Bar Yoach, which was a student of Gadi, found all the solution to mutual exclusion by checking all the possible solutions. They just generated at random automata, and they ran it for 2 weeks, and eventually it found all the 6 solutions for mutual exclusion up to 3 bits. So wonderful. But it's a clever idea, okay? There's a method called sketching, okay, by Bodic and Lazema, in which you have programs and you have some openings. You have some kind of pieces of the program which or not given, and then basically you can use SAT-solver to run on all the possibilities and complete the code. Okay? And that reduces synthesis into trying to synthesize small portions. And I think that's a good direction because, again, synthesis, by and large, is either of extremely high complexity or is undecidable if it's concurrent. And my own contribution, my student Gal Katz, or my ex-student Gal Katz, he graduated a few years ago, was to use genetic programming. Okay? I'll talk a little about that. So in genetic programming, what I do is that I run through different phases or different rounds, and each round I have a bunch of candidates. Okay? The first round consists of generating randomly a bunch of candidates to solve my problem. Okay? These are not completely random because I have to give not only the specification but some architecture. Say I want to generate a solution to the mutual exclusion problem. I showed not so good solution, but say I want to generate a solution for that. So I give you an architecture which consists of a loop and non-critical section, critical section, but I don't say how it solves it, and I have some random candidates. Then, in each round, I pick up some of the candidates. You see, I put it to the right. I kind of hand it to a mutator. A mutator takes the candidates and mutates the code. Okay? And then, what I do is, as I said, I use model checking as a feedback loop. I calculate the fitness, how well my candidates satisfy the property. Okay? So I have kind of a nice algorithm that tells me which properties hold or which almost hold. I'm not going to be, again, technical, and I have very, very little time to do that. But I get some kind of fitness markings, and then I return the best solution back to the pile. Not always the best. The best solution have a higher probability to be returned to the pile. And then I have another round and another round. Okay? And hopefully, eventually, I'll find some good solution. So here's the architecture of my system. I give a specification and a configuration as an input. And then a genetic programming engine generates some population of candidates. The model checker, and I call it enhanced model checker, it gives me some fitness results, and now I generate new programs and new candidates, and I go back in a loop, and hopefully, eventually I find something that satisfies all the properties. Okay? My program is represented as a tree, so I have a direct translation between a tree and the syntax. Okay? And here I just demonstrate one kind of mutation. I take the tree, the syntax tree, basically. I pick up a subtree, I remove it, and at random, I put a new subtree which match by type. Okay? Here is an example of a run. Okay? So each one of these examples going from, on the top from right to left and then left to right according to the arrows. Here is an example of generations where I start at random with something that doesn't really look like a solution to the mutual exclusion. This is one process, okay? The other process is symmetric trade. And at the end, on the bottom right, I have something which is a real solution to the mutual exclusion. In fact, not only we found all the solutions, we found new solutions, not for the simple problem, but for more complicated problems, which also attempt to be practical and to have less attempts to use each other's variables. What we achieved, okay, it's actually a human-assisted approach. Okay, we synthesize concurrent programs, although it's undecidable. Well, programs can be synthesized by humans, so they can be synthesized by a human-assisted approach. Okay, so our algorithm may fail, and then we need to help it. Okay, we managed to improve code, and we managed to find bugs. For example, in the AlphaCore algorithm, this is an algorithm which is used in many scheduler programs. And it's a very complicated algorithm. Automatically, we found a bug which appears in the journal paper, and we fixed it. Conclusions. So I started with model checking, and I hope I showed you that this touches on a lot of interesting topics. So it touches on automata or based on automata, game theory, logic, but other works, which I didn't have time to mention, also borders with complexity theory, compatibility, machine learning, AI, all kinds of things. So it's kind of an I'm stuck. Sorry. It has, I think, great impact. Nowadays, everybody who is serious in developing software and code is using model checking. Still, testing is by and large the most common method which is used to debug systems, but model checking is very successful. And there's many tools for doing that. And automatic synthesis, again, kind of, we know the theory. We moved from really high expectations that someone gives us the specification. Automatically, we synthesize code, and we're kind of stuck because of complexity, because of decidability. And nowadays, we realize that we have kind of to limit our expectation and to have human-assisted approach. Thank you.